Welcome back to the stream, folks, again. Some of you on Twitch might have seen that I just did a really quick video test, but now we're back, hopefully for real. So, welcome back to the shop. I was actually planning on getting started a little bit early today. I alluded to that on the last stream, but the schedule didn't quite work out that way. I thought it might be nice to do some filming with this other film crew that was here on stream, but that turned out to be kind of complicated and didn't really work out, so we ended up doing something slightly different. But I'm here still. And it sounds like Tuco's here too. Well, here's where the camera's pointing. Where's the cat? Oh, it's such a good fuzzball. I think he wants to play with the plastic bolt again. Oh, is that it? Oh, yeah, okay. That's my friend Zach. He's awesome. We have a pretty full house today with 3 cats and 2 humans. I gave him a hard one. I'm really looking forward to having a gimbal camera that can interact with this cat. Oh, we might have another cat visiting. Alright, so, there's a few things we could do on this stream. I was thinking we could continue where the last stream yesterday left off and try to get some LEDs wired on this winch. Since that's really the last, like, I would like to get one of these winches to the point where it's basically finished so that I can start like really seriously photographing that and turning that into videos. And then just like asynchronously go and build out the rest of the winches. So I've been excited about getting to the point where I can actually finally have all of the features that are supposed to be there all working. And so the one thing that I've been needing to do just hardware-wise, oh, how did that happen? I think I might have accidentally hit the camera switcher. Let's switch to this one anyway, that's what I wanted to do. I might have to move all of the cameras very slightly because a lot of things got rearranged this morning. Alright. That'll be alright. So, here's one of our WinchBot halves. And so on the last stream, I was trying to actually start mounting the indicator lights, which are actually facing inward right here, and they illuminate the innards of the winch through all of this translucent plastic and the ventilation slots. So I can take these screws out before they fall out on their own. This is one of the other parts of the project running here. This is an LED ring that goes on the flyer part of the robot, but it was nice to actually have some other LED set up here for debugging. So I tried to do that on the last stream, but then I ran into this problem where I really wanted these to be removable and did not have any suitable 4-pin connectors. So I went shopping, and there's a lot of options that either required a fancy crimping tool or were kind of expensive. One problem you run into is that there aren't nearly as many options for connectors that go from a wiring harness to another wiring harness as you see from like wires to a circuit board. So like I have the tools to do 4-pin JST, which are really common, from wires to a circuit board, but that doesn't really help me here. And then, so you get into somewhat specialty connectors, and some of those get kind of expensive. I had fun shopping, but it turns out the ones that I found that were actually good, well, so I won't talk about which ones are actually good quite yet. So first of all, I wanted to see like, well, what is just commonly available that I can get fast and for pretty cheap. And so I found these on Amazon with fast shipping, so I could just get them. And it turns out that they were still, like, I think, how much was this? Each pack of 10 was like $8, I think. 10 pairs. So less than $1 per. And so these are actually made and sold for LED lighting, so like exactly what we're using it for LED strips. And I have no idea how high quality these are. They seem all right just on first glance. The wires are tinned, they feel substantial. The insulation doesn't feel super grody right away. The pins are a little wobbly, like the alignment is not amazing. None of the tolerances are anything to write home about, but it seems like it's a decent, cheap connector. But I want to see if the wiring actually looks like it's any good before I really use these. So I got these just because like they seemed like they would be good enough, but I kept looking around, and then I noticed actually Adafruit has some that are awesome. So I ordered those, but that's with slower shipping, so I'll get those along with a bunch of other goodies next week. But I think these will be good enough for just like the first winch and getting that done, and then if I feel like it, I can go back and replace all the connectors with the nicer ones from Adafruit. So I think that's the plan. So, you know, I think the first thing I'm going to do is just, let's have these connectors mated together and just try measuring the resistance. We could do a nice 4-wire resistance measurement, but the first thing I'm going to do is just stick my plain old multimeter probes on it just to see if there is a horrendous problem. And then we can actually try running some current through it and see if it behaves like a wire or like something terrible made of aluminum or iron. This is the other thing that's great about ordering parts from Adafruit is I never worry about getting wire from Adafruit that isn't copper. It's really nice. So yeah, I'm looking forward to having those goodies. I'm just also impatient and thought that I would get the stuff with the same day shipping or the next day shipping or whatever it was that caused it to get here when I ordered them last night. Okay, meter. So just for a baseline with these probes touching each other, not very scientific, but you get something in the range of like 100, 200 milliohms. So just to see if there's a horrendous problem, let's first just try just to see what our contact is with the wire, or at least the plating. So I'm just touching the wire at 2 different points that are really close together, and I'm getting 0.1 ohms. And now at the other end of this, that's not bad so far, 0.2 ohms. That doesn't seem like it's a horrendous problem. Yeah, these seem like they'll probably be fine. But let's try running a little bit of current through it maybe. What's a good load for this? I've got a light bulb somewhere. I had the micro soldering tip on. I should switch back to the regular sized one for this light bulb. I don't think I need to solder the light bulb under a microscope. Well, the light bulb socket. Oh yeah, that's some classic Tuco right there. I've also got another cat right over here. Cloud has been roaming around by my feet. So he's probably gonna hang out on camera at some point. Oh my god, thank you, Zach. Oh yes. Well, this is also going to be a character on the stream. My cup full of cabbage and fake sausage. This is delicious. Oh, so we have some conductors here. Let's just try. I don't know why I'm recording this footage. What potential project will this footage of me soldering a random wiring harness to a light bulb come in handy for? These are actually all right. Like I mean, from a user experience point of view, like I still don't know if they're electrically that good, but like the tinning is nice. Like they're not painful to solder. They're like relatively pleasant objects. Better than I'm expecting so far. I guess I went into this with pretty low expectations after going through all that pain with the really sleazy breadboard wires that I was using before. Okay. Okay, let's not give this poor little bulb 24 volts. I think it's a 6-volt bulb. It's probably labeled, honestly. The label is really not intact. That's either 14 volts or 1.4 volts. That's probably 14 volts, but it might be a 6-volt bulb, so let's start with that. I'm just going to measure the voltage drop and see if it's not terrible. So let's start with 3 volts. Is not connected. Oh, there we go. A dim little glow. 6 volts. This is probably a 12-volt bulb. 12 volts. Cool. So that is drawing 200 milliamps, pretty much on the nose according to the power supplies meter. Oh man, this focus plane is tricky. Okay, so now we're just measuring voltage. What did I do? Oh, these were touching. Thanks, current limiting. Nice, 10 millivolts. And another 10 millivolts. I think these are fine. The only downside relative, I mean, the Adafruit ones definitely looked nicer. They were like brand name JST connectors. Also, They had all black wires, which should be a little bit less obtrusive. This color scheme is a little bit weird. I don't think this actually matches the wiring. Like, I don't think these colors will actually make sense with the LED strip, but it's fine. I think it'd be nice to actually just get something working so that we can move on and work on some of the software. I've also been feeling like it would just be really useful to have the LED strips just responding to changes in the software right now, because when I'm controlling it with the remote control, I don't really have any feedback. There's not like the web interface right in front of me with a bunch of charts. So having a little bit of LED feedback on the robots would actually be really nice. And so each winch has 2 little strips of LEDs, I think 7 LEDs each, pointed inward to kind of illuminate the guts of the winch. There's also a couple of little green LEDs on the circuit board. They were really bright, and I tried to cover them with some dark tape to block them a little bit. Okay, well this is great. So what this means is, well, I was about to say we could just like use this as an interchangeable system, and I could just like go ahead and solder this connector here and then like use this to test LED things and then whatever, but that isn't actually true if I haven't settled on whether I'm using these or the other ones, and I think I still like the other ones, or I'm going to like the other ones a little better when they arrive. But let's at least hook one of these up to the single winch that we're working on. So I think that means I'm going to bring it over to this desk and we can take a look at it here. There might also just be a brief cabbage and cat break. Isn't this cat awesome? Oh, you know, we should actually do the thing where we actually wind all the cord back up onto the winch again. Requires the remote control. You know, it's also possible where I'm doing this in completely the wrong order, because there were some other things that I thought we could do on stream involving putting some finishing touches on the Winch bot firmware. And it would actually be really nice to have it fully assembled for that. So in particular, there's actually a really nice tip. Actually, let me pull this up on the computer. There's a little comment discussion like just from earlier today that was super useful. But just a bit of advice about the PID loop I was implementing, and I think I said something on the last stream about how I didn't really see the point of filtering the derivative term for the PID loop, because it seemed like, you know, the PID loop itself was a low-pass filter, and that you would want to, and you know, so I didn't really see the utility of adding an additional filter there. But I think this discussion, like, it's you know, honestly more technical than I can get personally with signal processing and analog electronics, but it's a good pointer to the kind of mathematical framework that you want to have when approaching these kinds of problems. And it's also, I don't know, it helped to just see how it would be useful to have not just one sort of bandwidth, like the bandwidth of the control loop, but to also be able to have a lower bandwidth low-pass filter just for the derivative gain. Let's see if I can get this comment really quick. Yeah, here it is. Let's clear the screen a little bit. Yeah, so this was really useful from just like right now. So yeah, Ed says, you might find the derivative signals more useful in your control loop if you add a little filtering to it. Otherwise, it's super sensitive to noise. I'm no control loop expert, but I had to take a couple of control units and noticed anytime they gave a skeleton code for a PID, the DU signal was filtered. And yeah, so I kind of, like, I noticed that too, but I didn't really understand what was going on. And I think some like hands-on experimentation is like showing me that a little bit more. And yeah, so he goes on to say a PI controller, which is what we're doing when we have D set to 0. That's probably fine in this application, with the ramp rate limits especially. And yeah, we don't need this thing to be super fast. In fact, I'm trying to limit it to be relatively slow anyway, to limit the dynamic effects of the cord bouncing around. But yeah, it would be nice to have the option to tune in a full PID loop, and this seems like a pretty simple change that we could make to the firmware. So basically, if you just follow his suggestion and look at the code, let's see if this lines up. Yeah, so this is the actual PID loop. And in fact, often this stuff ends up being really obtuse looking because it's implemented using like really low-level arithmetic, like fixed point math, where you have to be really careful about integer overflows and underflows and having enough precision for the fastest and the slowest things that you want to represent and all that. But since this processor has hardware floating point, I'm just not shy about using floating point math everywhere, so it's been nice having a much simpler, and especially simpler to read and simpler for people to have like YouTube comment discussions about kind of control loop. And so, you know, these values map right to the values that we've been dealing with in the web interface because they're part of the same data structures. And this runs you know, at the same rate as all of our other control loops, which is 250 hertz in this case. And so each time we're, you know, so you can run through and kind of see what this does on each tick. We're grabbing the latest data from the sensors. There's one safety feature here where, you know, if we have gone a while without receiving a command from the computer, we shut down. There's another safety feature where we look at the limits on the force sensor. But the really core of this is like these couple of blocks of code here. So we've got linear velocity ramping, which that's like when you see the, well, let me demonstrate this here. Where is my controller? There it is. I guess I could use that thing that says joystick area, but I have a handheld joystick area. Oh, so yeah, that works. It's not the fastest thing, but I've also got this. And so we've got sensors. So if I just wiggle this, you can see that was the control stick in that brown line, and then that diagonal line there was the ramped velocity control. And so that is actually being done by this chunk of code right here, and just dealing with those same values. And then this is actually the PID loop. So we're calculating the velocity error, which is, let me actually try to get these side by side, if that's helpful. Oh, we have another cat visitor. Oh, you can just barely see her. Nose cam. Slight cat visit. All right. So velocity error, this first graph here corresponds to this calculation here on line 171. So that's just taking the output of the ramp generator and subtracting whatever the actual sensor velocity is. So when the motor is stalled, so like right now I can kind of take advantage of the fact that the PID loop doesn't respond very fast and just move this, and you can see at the very first part of that waveform, it's just following the ramp. And then once the motor actually starts to move, it starts to catch up, and then you see that jagged line as you're picking up all the physical noise from the sensor. And then, so here we're differentiating that, and it's really just, you know, one cycle minus the last cycle. And then to keep the units right, we're multiplying that by the tick rate. That's 250 hertz. Why is that the right thing to do? So it's right. So it's the derivative. So it's delta velocity over delta time, and so we're actually dividing by 1 over the tick rate. So I just simplified that to multiplying by the tick rate here, which of course makes it more complicated to explain. Hence the simplification. This is why programmers are terrible. And then here I'm calculating the integral, and that's similarly I'm just adding it, accumulating it tick by tick, but then also kind of keeping the time units scaled correctly. And this is a little bit easier to understand because you might be more used to doing like animation where you have to multiply the speed by the delta time and like you're integrating. This is a little more intuitive to me at least. And then, so those are calculating this graph, and this graph. So these three values are the inputs to the PID control loop. And so if I try to move this, you'll see the integral kind of accumulates, and it kind of accumulates this kind of stored error that has to then get dumped into the motor by the, via the integral gain. Whereas the derivative here is just super noisy. So we're talking about adding an additional filter here, and that would just be a nice firmware feature, and you could always get the equivalence of not having that filter just by setting the rate to 0 or 1 or whatever, depending on how it's scaled. So, and then he had a much more detailed explanation here, which is, this is like stuff that I kind of learned in the electrical engineering classes that I took, but not very well. Honestly, I'm really terrible at phasor analysis, so I'm like the last person who should explain it. But if you haven't come across this, it's basically a way of understanding and analyzing periodic signals using imaginary numbers. So, and then there's all this like weird terminology that electrical engineers built on top of the actual calculus that underpins it. So it's weird, but it's kind of a simple way, once you wrap your head around the basic parts of it, to understand electrical impedance and filters. And so, in fact, the whole idea of impedance as a, as something that's more than just resistance, as an imaginary number that can also represent capacitance or inductance, like this is why that works. It's just kind of complicated to actually understand why it works. So yeah, I thought that was a very useful little tangent to go on. And yeah, maybe we could just do that. So also on my to-do list for firmware things, besides this derivative gain filter, I was also just noticing that it would be nice to have a couple of additional safety features. I know there's already a bunch of safety features, but there's still a couple of things that can still fail in bad ways. So one thing that I've been planning on working into this, but I hadn't really gotten around to yet, is right now it has no failsafe for if the position sensor is not moving, but you're still powering the motor, which can happen for a handful of reasons. Like the sensor itself is broken, or, there's just like a stall in the motor, something is jammed, the motor controller's popped, like something has gone horribly wrong. And so there's probably some heuristic where you could say, like, if the PWM is over some threshold and the velocity is under some threshold, and this has been persisting for some other number of clock cycles or control loop ticks, then you shut down. And so I think that's going to be a useful feature to add. Also, yeah, actually, well, I had these as two separate to-do list items. So a sensor fail watchdog and that jam detector. I think those actually might be the same thing when it comes to position, but it would be nice to separately have a watchdog for if the force sensor fails, because you would want to stop if you can't tell if it's going to break itself due to a force overload. Robert says Cortex M4 also has saturating integer arithmetic. It's not super helpful here. Float is actually a lot more helpful, and I do have hardware float because this is a Cortex M4 F core. And yeah, this implementation is discrete time, so yeah, there's like it's accurate as the time step approaches 0, but if you want it to work in practice for large time steps and still not accumulate error, then you need to use a bunch of other advanced math that I would have to look up and don't understand nearly remotely well enough to explain. But there are different kinds of integrators that you can use that have better properties for this kind of thing if you're, especially if you're dealing with accumulative error. So yeah, maybe someone who understands that math better than I do can point out a good resource to that. But so far I've just been using a simple, very simple algorithms for this. And it's all right, but yeah, I'd certainly appreciate any pointers for improvements. All right, well maybe let's work on firmware, since I think that seems fun. And then we don't have to take the winch apart off the wall. So I was doing that from a Raspberry Pi. Oh, is that another cat in the background? I have this on the Raspberry Pi because it's much more convenient to run this particular toolchain on Linux than anywhere else. And it was easy just to have a small computer that I could plug into the winches to program them. If I was less lazy about developing out, kind of niceties for this platform, I'd probably have some way of flashing the firmware over the network. But so far you have to attach a USB cable to the debug interface. Yeah, we're basically talking about numerical integration and numerical differentiation. But yeah, it's all discrete time with data that we're measuring. All right, here's our bot firmware. So actually, let's take a gander at the protocol first. It's a little bit of a pain to make protocol breaking changes because there's absolutely no versioning mechanism in here yet, so you kind of have to be sure to update this and the controller side at the same time. So this is the structure full of parameters that come from the central controller to the winch on, well, effectively every control loop tick. And then we work these into our local decisions. I mean, ideally, we're running the local control loop in the winch at exactly the same rate as the control loop on the PC. And we could just do everything there. It's just, I don't want to trust the network to every detail of this. It seems a lot more foolproof to do this level of motor control actually locally in the same box as the motor and the sensors. So yeah, I think we could probably just add just having problems with this USB cable as always. So it's tempting to be like, I'm going to add this at the end of the structure because then it won't break compatibility, but it still actually will because it changes this other structure that one's embedded in. So I'm just going to break compatibility and add it probably right here. I think that's what I'll call this. Kind of following the same naming convention as this filter parameter. I'm going to remind myself which polarity these are, because people tend to do these super simple exponential IIR filters in either polarity where one is a slow, low bandwidth filter, like an infinitely slow filter, or 0 is an infinitely fast filter. And it helps to be specific about that. Hey, cat. All right, and let's go ahead and make the corresponding change in the Rust code. Not the JavaScript, it doesn't care. So this is a Rust file that defines a bunch of data structures which end up getting kind of plumbed all the way from UDP packets that are sent out by these microcontrollers up into higher level stuff that appears like in JSON in the user interface. And so as long as the data types and all the kind of structure padding and everything matches, then these will be compatible. So we're adding that after ramp velocity. So that's why you might have noticed the way this is laid out kind of strangely. I wanted to be sure that this part of the structure still left the next item on a 32-bit aligned boundary, because otherwise the C compiler would have actually added some padding there to be sure that the float is on the next 32-bit boundary. But I think the semantics of the serializer I'm using in Rust right now actually just packs everything tightly by default. So I would have actually had to add padding somewhere. I just wanted it to be explicit on both sides. Hey, Tuco. Oh yeah, that's a good point from Vavasor on chat, who says, I remember a series of videos for application in game dev that go through numerical integration techniques that was good. Yeah, actually, that's something I remember hearing a lot more about numerical integration that actually seemed applicable to what I was doing from friends who were doing game development than from the like really mathy people who tried to teach this stuff in the college courses I went to. So yeah, if you see resources designed for like how to apply linear algebra or calculus to game development, a lot of that stuff is actually really good because it focuses on the kinds of applications that are also useful for like robotics and certain types of signal processing and just generally like writing code that understands how to deal with motion and time. So anyway, I'm just going to basically copy this and then turn it into Rust code. I could be using something automated to manage this, but it hasn't really seemed worth setting up something that crosses languages and repositories for this so far, so I've just been maintaining it manually. Oops, I am having USB problems. Ramp velocity. Oh man, somehow I also just ended up with a bunch of cursors here. Great. That is a great feature of Sublime Text, but it's a little confusing if you manage to turn it on by accident. The multiple cursors is really great for doing mass edits of stuff. Okay. Diff filter param, and like while we're here, we might as well add some stuff so that we can edit this, right? So that right there is enough for this to know how to deal with all of the packet structure and how to actually get that into the data model used by the web app. So I think all we need to do is actually add it to the web interface. So that would be down here in Winch PID. And there's a separate little block for parameters that we can make it kind of hidden by default just to avoid changing stuff by accident. Let's just stick it up here. So we're calling this diff filter param. Oh, actually this isn't quite all the plumbing because this is not setting. So if we were getting data back from the winch, that would be all we need to do, just put it in the model and then we would get it. But since these are commands, these are actually generated by the controller, so we actually need to, like these other sliders are not changing, they're not changing like that byte in the packet directly. They're changing something in the parameter storage, which is then being used by the control loop. In this case, we're just sending it directly to the robot, but it doesn't have to be that way. And of course, the velocity we send out is something that we calculate. So in this case, okay, and we'll use the same name for this in params. And this will go between 0 and 1. Fairly small steps. Okay, so that on its own won't actually do anything useful. In fact, this will just cause errors when it tries to deserialize, because we would be giving... So the way this ends up working is this config slider here. There's such a stack of technology here, but I find it interesting to go all the way from like a modular web app down to like chips on a board talking to motor controllers. Oh, that's interesting. Robert says my structs aren't repr C, which means there's no guarantee on field ordering. I'm not sure that matters, because I'm not, like, I don't care about the in-memory representation of the Rust structs. I'm using serde to serialize them. So my serialization schematics aren't about like what the Rust compiler thinks. It's about what the bin code module that I'm using thinks. And so if there's something special I have to do for that, sure, but I'm actually just taking advantage of the way it packs the structures, which is a little bit weird. If that still doesn't answer your question, I'd appreciate an explanation, but I think that you might be assuming that I'm using the memory representation when I'm not. I can show you how that works though. Like, we could go through the whole stack. So like this thing here makes a, so this config slider is a React component. It's like right here, this looks like an HTML element. This is actually this thing that gets turned into JavaScript code by the kind of pre-compiler that runs on the code, Babel. And so this turns into an instantiation of this config slider component, which then, you know, is sort of this DOM element that in a lot of ways kind of, you know, you can treat it like HTML elements. You can nest other things. You can have attributes and properties. There's kind of a nicer model for dealing with how the components compose in terms of their life cycle and how they pass values. So I don't know, it's still something I'm learning, but it seems super useful so far, and I've already been finding some good ways to take advantage of its features here. So that config slider component is in this file. And in fact, it just wraps an HTML5 like slider input here. There's another component which just draws text from the config. But mostly what we're here for is to add this event handler so that when we slide this around, there's a lot going on here actually. So we start out by converting the value from the slider back into a JavaScript number. It gets converted into a string because DOM, and so we have a number again. And then we use this setByPath function. So what this is actually doing is it takes this this path, which is in this props.item. So that's going to be something like params.diffFilterParam. It could also be something more like, do we have a better example? I don't remember where the other example was, but it could be like a list. It's just, you know, a path that describes something within a JSON object and array hierarchy. So if it's a string key, we assume it's an object. If it's a numeric key, we assume it's an array. And that just creates the elements as necessary. So we end up just converting that combination of a path and an item into kind of a dense JSON tree. So, where was I? Yeah, so if this is something like set by path, and then, oh geez, this keyboard is so annoying. So if this was like props.foo, and then we were setting that to 5.0, then we would actually get this object that looks like props, and then foo 5.0. You know, if this was like props.foo.5 or something, then this would actually look like, you know, something like that, where we just have this kind of skeleton JSON thing, which has the same overall structure as that config blob, but it doesn't have to have all of it. And then we send that in this update config message to the server. That goes through this WebSocket layer, which I'm not going to go into detail right now because it's kind of transparent at this point. When we send this update config message, the WebSocket server will, allow that through as a command if we're authenticated, and that will end up over here in the controller as an update config message. And so at this point, the updates will be serialized, well, deserialized into a kind of loosely typed JSON blob that has already been parsed. So we know it's valid JSON, we just don't really know what structure it is. So it hasn't been fit into the strongly typed Rust structures that we're using here yet. But then we kind of merge it with the existing configuration, which is a bit of a dirty operation, but I kind of like the overall effect. It works by taking the serialized Rust structures that represent the configuration, deserializing them into an in-memory JSON object tree, and then merging those recursively and then reserializing to that in-memory representation. So there's really 3 different representations we're dealing with here for everything, for all of these data structures. There's JSON used by the web interface, the WebSockets protocol in general, outside the server, just the outside world. There's UDP used by the robots themselves. And then there's the in-memory representation in Rust. And so we don't really care about the in-memory representation, but we care about those 2 endpoints. And so both of those are handled by 2 different serialization, deserialization modules in Rust. And yeah, so I don't need direct compatibility between those structures because there's like the only places where I care about the binary is on the wire, like the UDP protocol, and it just makes sense to serialize and deserialize there. It doesn't seem like that single interface should dictate the entire in-memory structure of the data, as long as I have a nice way of getting it back and forth, and using these 2 serializer modules, so JSON on one side and then bin code on the other side. And so bin code, it's not, I'm like kind of using it a little bit off-label. Like it's intended more of like an RPC thing, but it's like, it's just an extremely straightforward serialization protocol, and most objects are just kind of concatenations of their contents. And so that's how I'm getting away with this. Where's merge? Yeah. Merge, I mean, I don't know how deep I want to go into this rabbit hole, but this is maybe a good explanation or a good example of the kind of object model stuff that's going on here. So config is really just all the stuff we have that doesn't change that often. Like, it's basically stuff that changes, when there's, when someone presses a button, when I change something in the web interface, when I drag a slider, but not just like every clock cycle as a result of a control loop. And this stuff is also persisted to a file that's stored in YAML, which is another weird kind of object markup sort of language that is mostly JSON compatible, but much nicer to edit by hand than JSON. Here it is. This is the config file. So like our calibrator, we ran a calibrator last time in the web interface, and it saved this data. So all of this gets automatically annotated by these derivation lines with a bunch of other just automatically generated methods for doing things that sort of funnel these values into and out of these deserializer and serializer components. Pardon me. Yeah, and so when I drag one of those sliders to control the parameter rate, so just to resume the UR here, we've been in, so we're talking about what happens when you drag this slider. It sends a configuration update to this diff filter param, and that ends up right over here. So we have to add something to this bot parameter structure, and then we're also going to need to add it to the configuration file. Or otherwise it's going to complain on startup. Maybe this is a good time to kill the existing server process. Control-C. You know, Control-C is not the most reliable thing in the SSH for Windows, oddly enough. Do I have, like, PS? Oh, or maybe it's my, maybe it's the keyboard problem, the thing that we're already sure is not reliable. Oh yeah, that's fine. Sorry, SSH, it wasn't your fault this time. Alright. So, now it's not going to be writing to the config file while I'm trying to edit it. So, what was this called? Did I have that in my paste buffer? No. Yeah, diff filter param. I'm also using F64, so double precision floats for all of this. Mostly not because I need the precision. The only stuff where I really want it to be F64 is stuff that's dealing with time. Because the number, like when you want like millisecond precision on the number of milliseconds since 1970, it's nice to have double precision. But for everything else, float 32 would be enough. It's just that on modern processors, F64 is pretty much just as fast, and so it's better if I am consistent with the code that's in like the bulk of this server. But I'm using 32-bit for the wire protocol because that's what's good on the microcontroller, so I just convert it right at the edge there. In case you were wondering about the data types. Okay, so now that'll get it into here. I still need to add it to the config file. Just set it to anything as long as it parses. And because as soon as I recompile this, it's going to include this in its model for what that config file needs to include. So it would not like the config file. It would refuse to load it if it didn't have that. And then we already added it to the actual wire protocol by adding it to this winch motor control structure. So the missing piece is actually just to connect the two together. And that happens in the controller when we're sending out winch commands as a result of every single control loop iteration. You'll notice we calculate a velocity here and send it out. But most of these are just copied from the params because they don't change from cycle to cycle. But we're doing the unit conversions here, since that seemed like a good place to do it, since the firmware doesn't really want to have to deal with calibration at all. But inside the whole server, it's nice to keep it in SI units when you can. But these are unitless, so no conversion. I think we can just compile that server now. Cabbage break. Oh yeah, rounded off timestamps are not fun. Yeah, no, floating point time is actually kind of hazardous. Like, not quite as much with 64-bit, but like operating systems programmers have to be very paranoid about how time is represented, because if you want your program to keep running for years and still care about nanoseconds, then you've got something to consider. Yeah, floating point time is not the best representation, but it's convenient. So I tend to use integer representations in very low-level code, and then design APIs around floats. Or design APIs that have the option to have floats. Why don't I have diff filter param? How do I not have diff filter param? Didn't I add that? Oh, wait. I added it to winch motor control, but not winch command. Yeah, that was the wrong place, actually. These are outputs from the motor controller. Oops. Okay, that's easy to fix. Better to notice it now. This goes up here after accelerate. Is that where I put it over here? No, I put it in the wrong place over here too. I would have noticed that fast enough, I hope. Yeah, so that goes over here in winch command, not winch motor control. So let's just make sure these are matched up again. So winch command, it would be nice to be doing this automatically, but they're in separate repositories and in different languages, so... And this is like one of those, like, I've said this a couple times, but this is probably the last protocol change, so... Just trying to get them all in before it's as much of a hassle, because, you know, now it's updating one thing instead of 6 things. Well, 2 things instead of 6 things. Because I have 4 winch bots, the flyer, and the central controller, which all need to be updated if the protocol changes. I mean, maybe if I'm only changing the winch protocol, I don't update everything, but I would want to be very careful with that. Okay, that seems fine. Actually, I mean, there's kind of a trapdoor for that. Right now, I've been a little bit cowboy with the protocol changes because I can just change every instance of this thing that exists pretty easily by just reflashing this thing. But yeah, if I need to do something a little bit more controlled with protocol versioning later, I can just change the IDs on these commands. And it's only an 8-bit space, so I don't want to burn them too quickly. But that does give me a way of making a command incompatible so that I don't accidentally send something that would be interpreted wrongly and give the motor controller a bad command. Okay, so we got a new version of our Rust server, which will be ready when we've got our firmware changed. We don't actually want to run this right now. Alright. So let's put this controller away and look at the firmware. So that gave us this diff filter param in winch command. Yeah, and we don't need any additional state. It just means that now... So one thing is changing. So previously, this velocity error was kind of a write-only thing. It gets written to every single tick of our motor control loop. And the diff was the same. It got written to every tick, whereas the integral actually stored state. It would get added to. So we had to be careful to zero that out anytime the motor controller needed a reset. So we'll have to do that with the diff gain as well this time, or the diff accumulator, I guess it is now. Filter state. Okay, so let's do that first, maybe. Have I centralized that? Yeah, so here's where the motor control state is reset. In fact, some of this used to be below there because I just didn't really care about having this calculated if the control loop wasn't if it was like halted. But then I added it back up there because I wanted to be able to see these values on the graph. It's probably fine to keep clobbering that to 0. It's tempting to move this down there just to avoid what seems like it might be a race condition, but I don't think that's actually a race condition because this should be higher priority than anything that's dealing with UDP packets. Like, definitely higher priority than the network stuff. So, yeah, so let's just add the filter up here. I think that's all we need. So, just to I'm going to make sure we're not referencing PWM anywhere else to set it to 0. But I'm pretty sure this is already centralized. So we've got that down there. This whole file is actually still pretty small. That's where we actually enable the motor, only way down there. So if we never make it there, the H bridge stays off. Yeah, that's the only place we have halting logic, so that's cool. So, and what was the polarity of that other filter? This is that other filter we were dealing with. So it had this param. I was trying to be careful to avoid filters that had a parameter set to exactly 0 or exactly 1 in this case, because this is like one of the inputs to a safety feature. So I wanted to try to avoid like, oh, if this gets clobbered to 0 or well, clobbered to 0 wouldn't be a bad thing, but if it got set to 1, the filter would never converge. And so you could still sabotage this, of course, by giving it an unrealistic force limit or setting this to something very close to 1, but that just seemed to be an easy way of ruling out one really silly failure mode. But yeah, so this is using 1 minus param, which seems fine. Let's break this up slightly. I don't even think it's worth storing the unfiltered in the status structure, because it's just going to be varying so quickly that it's not really that useful to monitor that on the other end of the network connection. Like, the filtered result is a lot more useful. So I'm just going to keep that as a local variable, and the compiler can do what it wants with that. Where do I get the params from here? Oh yeah, that was in winchstat.command.
Micah?
Mm-hmm.
Do you have a USB-C charger?
I do not have a USB-C. I'm sorry.
Okay. Wait.
Sorry. Oh, that's what I call the stiff filter. Oh man, the things you do for C compilers. I'm just thinking about how to arrange this to be compact without being especially gross. I could refactor the entire motor controller, but I don't think it needs that. Yeah, I think this is fine. I often find myself writing code where I'm very particular about where I do loads and stores from structure, or from data structures that are accessed behind pointers, because the compiler, at least in C, is not really allowed to do especially deep reasoning about stuff that you access via pointers across function boundaries. And so I find myself often being really strict about having a pattern where I read variables from the shared structure once, manipulate them as much as I want, store the result exactly once, and keep the local copy if I still want to do stuff with it afterwards, but don't reread it again from the shared structure, because all of those loads and stores, it's like hard to guarantee that they can get optimized out. So, whereas like once something is in a local, the compiler can actually do all sorts of clever stuff with it. Oh geez. Just reading Robert's comment in chat, who says, for maximum hilarity, a thing I worked on once ended up with int64.js and capital int64.js. And yeah, so I've actually had that case confusion show up before. Actually, I had a build fail because my current working directory had a different case in it than the Git repo had, or something along those lines. They're somewhere stored in the project configuration, and they were the same except for case. And this was because of the case that I used when changing directory to the project before making it. Yeah, so Robert says if you use LTO and don't break the strict aliasing rules, the compiler can optimize it in theory. Yes, that's a lot of ifs, and I still don't know anybody who uses LTO on like a reasonably sized project. I certainly loved using LTO at Siftio. So for anybody who doesn't know, LTO is link time optimization. So it's sort of like you compile all your .c files or all your .cpp files into .os, and then you compile the .os again. It's not quite that severe, but it basically involves allowing the linker to do a lot of the same kinds of inter-procedure optimizations and dead code analysis and stuff like that that the compiler is capable of doing. But once you actually have all of the pieces for the whole program, then you can make much more kind of sweeping decisions about throwing away stuff that you don't need, or simplifying stuff down, or changing the representations of things. Yeah, and it's kind of practical to do this on small projects, but large projects like LTO, I have not seen it be super practical, but then again, I've not worked on it in a while, so if it is more practical on large projects, that's really cool, and I might like to try that. Oh, and Ed, whose comment inspired me to do this, is here in chat. Hi, nice to see you. Thanks for the inspiration. So yeah, that's kind of what I'm doing here. This is also, you might notice, not strict C code. I'm using some extensions, like being able to declare variables not at the top of blocks, because that's a silly rule. But yeah. So we've got this broken down in a couple pieces. We're kind of loading all the variables we rely on and doing some initial calculations to get the velocity error, the unfiltered derivative, and then we're just loading the previous value for the filtered derivative into a local and then operating on it here. And I wanted these to be separate so that I could refer to this without having to pull it out of the structure again. And then down here, we're just writing everything back. And then we continue to use those locals again down here for the PID loop if we get that far. So that is one of the things I wanted to add to the firmware. Let's see if that compiles. And better yet, let's see if we can actually communicate with the microcontroller still. Yeah, C99 is the thing. It's like the good kind of C. But I guess what I mean isn't standard C. I mean, I guess I have an old-fashioned view of that. For me, C99 is like newfangled C that people complain about, not standard C, but I like it, so. Missing period. Ain't that the truth? Okay, so I still have some safety features on the to-do list that I want to add, but let's see if we can test what we got so far. I need to plug the Raspberry into the winch. Oh, that's not a bad shot. Hey, Tuco. Oh. Hey, Tuke. Oh, are you coming over here, buddy? Oh. Hey. Ooh. Hey. You trying to get off? Yeah. Oh well, that didn't work. I think this is the shot we're looking for. Oh, I was just realizing I had a window covering up the YouTube chat, and I didn't see this until now, but Concrete on the YouTube chat says Tuco is super cute. I agree. Super cute cat. So this is kind of an open source adaptation of a bunch of code TI released for these chips they made. Oh, we got another cat. Luna's coming over here. I should turn off that soldering iron, Luna. Hey, girl. Do you want to behold? Luna is so small. Oh, you really don't like that. Okay, that's cool. Okay, 0 for 2. Actually, that's not true, because the film shoot that happened earlier today, we got a lot of really good cat photos, but I think I've used up all my cat karma today. Alright, programming the firmwares. Firmware's programmed. Let's run the cargoes. Copy the URLs. Why you disconnected? we go. I think I needed a fresh browser. That browser had gone stale from sitting out too long. I think we're still good. So now we have PID, gains. Oh, and we are still using the compiled version of the web interface that has not been updated, so I think I might just recompile the web interface. You can also run kind of an online development server that just compiles it dynamically, which is nice if you're making a bunch of changes, but right now I think I'm just going to run this. Where's the cat now? Oh, he's way over there. Optimized production build. Optimized production build sure is slow. Look at that, we got a filter rate. So, I'm going to start out with only proportional gain. And let's set this to, I don't know, something. And let's just see if we can watch. Might help to have the controller on. Okay, so we want to clean this up. Oh, look at that. So that just filters out all that noise, and let's see what happens when the graph scales back down. Still a lot of noise. I think what we want is a sweet spot where, so like there's going to be noise no matter what we do with this kind of filter, it just is going to be at a much reduced amplitude. I think what we're really looking for is something where we have a useful signal there and not just the noise. So I think with the derivative gain, we'd be looking for something where we get a little burst of activity when the error changes, when, you know, not just has a noise burst, but is actually moving in one direction more than the other for some brief period of time. That's still pretty bumpy, but you see a little bit of peaks coming up there. And this probably has some, like, might be interesting to look at this in the frequency domain, because I don't even know where spectrally you're going to see the most interesting features. Oh, that's interesting. Robert says that Firefox is compiled with LTO. I believe it. It just probably takes a long time, but it's, you know, it's worth it. I mean, the filter seems to be working. It's hard to tell if it's actually useful. But, you know, whatever, we have it. We can play with it now. See, like that might have been nice. Let's actually try adding some of this then. So, proportional gain is kind of high right now. Let's see what happens if we have a low proportional gain. Oh, see, that time. That's interesting. This is still... Like, it seems like I have more headroom in the proportional gain than I would have thought. It's actually maybe more stable since I've got a fairly heavy weight on it right now. So, I should really be tuning the PID loop with the proper weight on this. But I think I also want to make sure that it can work all right with a range of weights, because the actual tension that a particular winch is going to see in the cord depends on where the flyer is in the room. Edward's asking if the velocity is measured directly or estimated from a position sensor. It is estimated from a position sensor. The hardware unit I'm using does have an instantaneous velocity, but when I tried graphing that, that seemed super noisy. Or rather, it would have these kind of like weird spikes that didn't seem to be correlated with any kind of actual motion. So I didn't really get around to debugging that, and so currently I'm just on every tick. Like, so the hardware latches the output of the quadrature encoder counter, and so from a hardware timer, we're getting these regular samples, and then I subtract those in software. Robert is asking if I'm using the derivative of the measurement or the derivative of the set point minus the measurement. I'm using the derivative of the set point minus the measurement, but if the set point isn't changing, I don't see why those should be any different. Oh, okay, that's only for if you're changing the set point. It doesn't seem right. Because I think you, like, don't you want it to respond to changes in the set point? Isn't that part of the point here? Like, I don't see why you would separate those two sides of the velocity error calculation. This responds very slowly. I could also maybe turn up the acceleration ramp rate just to make it easier to tune the PID. So let's just try maxing that out and turning this all the way down just to get a sense for that. That ramp rate is still finite, but it's faster. That's interesting, isn't it? So velocity error derivative is pretty spazzy. Let's see what happens if I play with that filter. Probably need to change the scaling on that. I really should switch to the development server on this because the rebuilds take way too long. Okay, so that's npm start. Okay, now this will just auto-reload when we make changes to the code. because this really needs to be centered. I mean, the useful range of that slider is just right around 1, really. Like, what did I set the other slider to? That was in winch sensors. Yeah, that I only went from 0.8 to 1 on that one, in steps of 1 times 10 to the minus 4th. There we go. That thing where the scroll bar is covering up the numbers on the right are that's kind of annoying. Well. Oh, see, that actually looks a little nicer. Maybe we do need to zoom in on this. See, that's nicer, right? That is still pretty spazzy. Yeah, I think we just need this to be much closer to 1. Why am I using the inverse? The 1 minus. I think... I don't know where I saw that convention, but I don't really like it. I think I might just switch the polarity. And doing it now is probably going to be less painful than doing it later. So while we're breaking everything protocol-wise, maybe I'll break that, so I can just make these numbers close to 0 instead of close to 1, which are much easier to work with. You can basically, anytime Robert has a troll tag in his comment, we can just filter that out. Can we do that programmatically? Is that like a hashtag we can mute? Yeah, I think that would be better. Where do I actually document? I mean, I just now added to the header file, like, which way is which, so I'm just gonna reverse that. Okay, I'm reversing these. That's force filter param and diff filter param. So that would be bad if I just made that change in isolation, but of course I'm going to swap the config file around too. Let's Control-C that server so it doesn't send out motor control commands with bad values. Okay, so over here I want to change the config file and the two UIs. Oh, this really doesn't need to be that exact. this is not that well tuned either. Just set those to about there. And I don't even know how useful it's going to be at such a low rate, but whatever. We'll experiment with it. It's just like if that's trying to help us respond faster, then, well, yeah. I mean, we just need it to not oscillate, right? Like chattering controls in the motor are bad, but that's our main thing to avoid at this point with the tuning. Okay. This is not logged in because running the server again changes the key. Right. Okay, so if you set it all the way to 0, then the firmware is like no, and it disables the filter entirely. But if you set it to a very small value, then you have a really slow... Oh, I also need to change the calibration instructions, don't I? Yeah, because this also assumed that slow was near 1. Something like that. That takes a long time to settle. That's way too slow for anything useful. That's maybe better. Okay. Let's look at the PID loop. Yeah, so now it's actually catching these as, you know, constant derivative. The chattering there was from me kind of hesitating with the control stick. If I just slam it to one side and let the ramping deal with it, then I get these nice little square waves. Which is also the case all the way up here. Alright, maybe I don't need to go quite so low. Let's increase the girth of our slider here. Do we dare to go all the way to 0.2? Okay, so that's fine all the way up here. Let's try actually turning on the motor now. So let's add some proportional gain. I mean, part of the problem might just be there might actually be like legit a lot of noise in the system because of all the vibration from the cord. Oh yeah, it looks like that's what Edward just said in the chat. Yeah, but I'm glad we added it to the system at least. Like now we've got the parameters we need to tweak it. Like we can always just turn it off to 0, and I don't really think we'll miss the CPU cycles we're spending calculating it. So I'm not going to spend a ton of time tuning the system right now because many other things will change that will require the tuning to be slightly different probably, but we could at least have these tools kind of debugged. What is this like if we make it much slower? Well, what is that like if we actually send some of that to the motor? Because so far that gain has been 0. More power. I also have this scaled much lower than the other gains, which could be part of it. Okay, let me change the scale on that to be more comparable with the other gains. From 0.01 to 0.2. I'm just going to turn it up until it breaks and then turn it back a little. It's already starting to break, honestly. Well, I don't know. I mean, that's pretty noisy, right? Yeah, I don't know. You can kind of hear the motor chirping. So then what happens if I just add a slower filter? Takes away the chirping. That's not bad. I'm happy to have this tool in the arsenal. Also, right now it's a little hard to like race the motor around without just ending up dumping all the energy at the bottom of the winch route right here. It'll be a little nicer once I have something I can move around in 3 whole dimensions. And then I can have a better idea of tuning this maybe. But that's what we got so far. I'm going to turn this a little bit down for now. And turn this a little bit up. And then maybe we'll have a tuning that's good enough for the moment. A lot of like kind of thing going on. Like I think it's oscillating as it's like with the load moving around, which might be something that the integral gain is doing. Honestly, what is it like if I just give it too much integral gain? That wasn't a good test because I was not driving it smoothly. So there it is, me just trying to drive it smoothly, and you can see it was a little warbly, warbly, warbly up and down, but not too bad. Can I go higher? Wow, that was fast. Okay, where are the downsides there? That was actually kind of nice. Hee. Yeah, there's maybe a little bit of that oscillation, but maybe that's a problem with having too much integral relative to the proportional gain in the system. Let's turn that down a little bit and see if we can go higher with proportional. That's a little oscillating. I think it might be too much integral. Anyway, you could just continuously fuss with these, and like I said, there are better times to fuss with this, so maybe it's time to move on. So, that watchdog timer, I already have something that's similar. Well, a couple of things actually. Maybe it'd be wise to check this in. No. I don't need to push that yet. Okay, so let's move on to that other safety feature. Maybe first a demonstration of why it's useful to have this. Let me show you right now what happens if you just get a jam that causes the sensor to no longer read anything that's moving when it is actually in fact moving. Alright, so there's the bot. Let's go to another camera. Tuco is back up here. Let's use this camera for Tuc. Let's just take the DSLR off the magic arm. Oh yeah, somebody was asking about this recently, and it is super handy. It needs a decent amount of care since it's kind of a, it's a mechanical device that relies on tension. So as you might imagine, it needs to be adjusted every so often, but it's really good for just getting the camera into weird positions. But it seemed also worth having a regular tripod around for times like this. All right. Try not to knock anything over here. This needs to be taller. Oh, gotta appreciate that. Alright, so there's the winch bot happily winching along. But let's say something got jammed, like let's say it's lowering the cord. Let's say this got jammed and it stopped spinning. It's just going to keep going until I stop it. It currently has no features that prevent it from just getting kind of a runaway PID loop in that case. Since I'm telling it to move, it's just kind of out of control there. So there are a few ways I can imagine doing it. The simplest thing that came to mind is that I'm looking for just a flat-out stuck position sensor. So something where the sensor is not moving at all or moving very little, and the PWM command is over some threshold. That seemed to be the best thing that I would notice. Oh yeah, Edward said, I keep forgetting the axis scaling is dynamic. It makes the filtered signal look way noisier than it actually is. Yeah, you see that a lot in this force feedback sensor especially. Yeah, if I go back to that, it looks like there's lots of noise, but if I actually make the axes visible, that scaled from 1.58 kilograms to 1.59 kilograms. And just touching this a little bit changes that significantly. And now we're not measuring, well, now we're measuring like a different magnitude of vibration. We're measuring this cord moving around a little bit. Yeah. And then those abrupt starts and stop, or the abrupt stops rather, were causing overvoltage resets, which I still might have to do something about. If I keep seeing those, I might just have to design a little clamping circuit board and add that on. It's just one of those problems where it doesn't seem like there's any benefit to trying to go and solve it right now, because like I'm not designing a circuit board that it would be easy to add that feature to. That would require an additional thing that I have to design and add on. I don't think it would be as simple as just adding a diode, because I don't think I could reliably have a diode that clamps at an accurate enough voltage for this application, but maybe I'm wrong about that. Maybe there's a diode that would fit this just right. In any case, partly what I'm relying on to not get into that situation is just moving it much less abruptly, and so these days you're seeing that when the PID loop is misbehaving. So let's go back to firmware land. I also wanted a watchdog timer for if the force sensor is not responding. I wonder, I think I might have even already started to code that. Not. So I do have this one counter up here that counts the number of ticks since we've seen a new command. I could just add something simple or similar for the force sensor. I've got a counter up there that we can just read to see if there's a new force sensor reading. I like having counters that are... This is maybe a good tangent to talk about a concurrency strategy. So one way to handle this, for example, would be to have a Boolean flag that I set here in the Winch force sensor callback that says, you've had a new reading. And then somebody else has to have responsibility to say, no, it's not new anymore, I'm done with it, and say, that's equal to false now. Now you've got a race condition. And so one way to avoid that is to actually have one side only send values and the other side only receive them. So in this case, the interrupt handler is keeping a counter up to date, but nobody else writes to the counter, just this interrupt handler. And then elsewhere, I can read from that counter, and there isn't some kind of race condition there, because at that moment where I sample the counter, that is just a single atomic moment where something has happened or hasn't happened. And if it hasn't happened, I can record the fact that it hasn't happened accurately and then handle it next time. And if it has happened, then I can record the fact that I've handled it without precluding the fact that something else might have arrived new, between handling it and writing down that you've handled it. So I might knock this off the table, so I should probably finish it too. Yeah, so that's kind of the same strategy we're using down here. And this is just a local static variable. So like the scope here is local, so this is the only place that can access it, but it's allocated globally, which is kind of useful for this situation, assuming you don't need multiple instances of this whole thing. Okay, so all the limits are down here. So let's also add a... Okay, so here's the other kind of safety feature, timers. This is the one we've actually been running into a lot because the PID loop has not been super well tuned. But if we were trying to just halt it by letting up on all the controls, sending a velocity of 0, but the PID loop is pretty slow to shut down, then this timer will actually start ticking out. And after only a quarter second, which maybe I should increase this, because this has been a little aggressive. Maybe I want it to be like a third of a second. Let's try a third. Because yeah, after this amount of time, it'll actually just shut off the H-bridge and let the motor coast. So, and then it keeps doing that until we give it a non-zero command again. And then so this is just for if the central computer stops talking. We expect it to send commands pretty frequently, but it's not running on a hard real-time operating system, so I don't want to make this too nitpicky, but it really should be getting these packets very frequently. Ideally at the same rate we're doing our control loop interrupt. Okay, so the rates we're dealing with here, the force sensor should be updating at 80 Hertz. The main control loop is 250 Hertz. But it's, we want like an integer multiple, and we also want to think about, when these two things are kind of out of phase, like what's the worst case. And also the force sensor is one of those things where we don't need to respond quite as fast, but we still need it to be, something that can actually prevent things from breaking, hopefully. So let's make this a lot more conservative, but still pretty good. And this is detecting if the force sensor has a problem, so maybe like 10 cycles or something. Because that's just asking... That's actually probably good, because the force sensor has a different mode it can go into where it can be giving us data at 10 Hertz instead of 80 Hertz. And so I think we do actually want to notice if it's giving us data that slowly and treat that as an error. So having that boundary set at like 25 Hertz actually seems pretty good. Yeah, so it's pretty easy to express this as a frequency here. I just want to have an idea of what it actually looks like in integer terms, because we are going to be dealing with it as an integer number of clock ticks here. Control loop clock ticks, not CPU clock ticks, of course. Yeah, let's just use like 20. Is that a nice number? That isn't a nice number, is it? 25 would be much nicer. That's 12.5. Meh, whatever. Let's do 25. Okay. let's use hertz instead of samples per second here. I think I was mentally copying the datasheet terminology, which I haven't even read recently, but I think hertz is a little easier to think about. Then the other thing is that I guess I want to think of it as like a jam detector. Like the force sensor isn't moving, but the PWM is non-zero. What should I really call this? Position sensor jam. That's fine. And so it's, there's kind of a boundary between like parameters that I would want to be very dynamic, like in the network protocol, versus parameters that I would want to be kind of baked into the firmware. And that's kind of a line between this kind of level of autonomy that the device should have just to keep from breaking itself in its environment versus the tuning that I want to have for all the kind of full-featured parts of it. So because this is like a low-level safety feature, I want to just choose like fairly conservative settings and kind of bake those into the firmware. The force sensor is kind of an exception to that because I figure I'll have to tweak that a lot, so the values for the force sensor come from the host. Okay. So let's not worry about PWM values that are pretty low because whatever, but let's say it's over like 0.4, scaled from 0 to 1. And velocity. So, and this is going to be in units of encoder ticks per second. Which is, like, that unit tends to be very large because the encoder ticks are really small. Like, what is our calibration right now? This is meters per encoder tick. 33 micrometers? I mean, these are like 300 count per revolution encoders. There's like way more resolution there than we need. So, in terms of actual counts, well, can we read the actual velocity in counts while I'm just moving it really slowly, like maybe simulating a jam condition, and just see what that looks like? Because I'm a little worried about conditions where like it's mostly jammed, but there's still something kind of rubbing up against the sensor and it's moving a little bit, so I want there to be a non-zero threshold there. So yeah, this position and velocity are relevant. If I just spin this, the motor moves in the opposite direction because velocity error. Moving this pretty slowly, I don't know, it's like a couple thousand. Yeah, let's set this to like 200 or something. And then we also want a duration, because this is not an instantaneous phenomenon necessarily. We want it to persist for at least a few clock ticks. Maybe 1/10 of a second. Because these are kind of specific. I mean, that seems too quick, maybe. Let's go back to 1/4 second. Might be too twitchy, but we can fuss with it. Oops. Okay, so can we open another copy of this? Because I kind of want to have the top of the file next door. Yeah. So let's apply this max ticks since last force reading. So same thing we're doing up here. We need a variable to store the previous thing that we read from that counter. And then another counter that just keeps track of the number of ticks that have gone by with the conditions fulfilled. And where is this? The force dot counter. I like counters. It's a good way of just sending a stream of delta values somewhere. Like, this many things happened. A non-zero number of things happened. A lot of the time you just want to know if a non-zero number of things happened pretty reliably. So sticking counters into atomically read and written 32-bit variables is pretty nice. Yes, and then we're just looking, we don't care how many commands have happened, we just care that something has happened, and we'll reset the timer. This is silly repetitive code, but I think we're only going to have 2 things that are just like this. And the other one is going to be a slightly more complicated check. The jam detection, I guess, can go below this. Let's change this slightly. Because I kind of want to set will halt equals false, and will halt doesn't even exist yet, so let's start here. Yeah, same thing. These could all be the same if. It just seemed easier to read if I split it up like this. Oh no. Didn't want any of that. So we're looking at the actual PWM value, which I think we want to use the last one. Yeah, I think the thing is this stuff can happen right away, whereas the halt detector kind of wants this stuff to be calculated, and I think we want the velocity, so let's just move this down. Figuring out what order this stuff goes in. I want to be above that. Okay. Yeah, and this will use the previous cycle's PWM value, because the PWM is the last thing we calculate. Like, obviously we need to use the previous cycle's value. Or we would just calculate the jam detection value, which wouldn't kick in until the next cycle, so it's 6 of one, half dozen of the other. Can I use ABS here? This is another thing I over stress out in C code, like, oh man, can I even call this without it turning into a huge, like, library call thing? I mean, with hardware float, you would think they would have a compiler intrinsic for this. I do want FABSF, though, so that this isn't the double precision version. I don't know, man, that makes me nervous. Calling a function with floating point values? Can we do that in 2017? Where's that velocity? That velocity... Oh, that velocity was from way up here. That is completely unfiltered. We had that all along. That's fine. Okay. So we don't need the velocity error. We do want this to be above where the ramp velocity is taken into account. And this is kind of the next stage of that. Like, if we've been in this halt state for too long, then we just turn off the motor controller. I kind of want this to go directly here, honestly. Is there any way I can merge these two concepts of the jam detector and this motor halt? Because otherwise they're going to cascade, like this detector will run, and then when it actually trips, then it'll start this timer. But I think things are already pretty well going badly by the time this timer will have expired, so I think we want to go right to the motor actually being halted. Well, yeah, I mean, something is really bad if this case has happened. Like, we don't want to ramp the motor slowly to 0, we just want it to turn off. So maybe we do want to combine it with this case. Yeah, it would be nice to split up this function. Right now I'm thinking about just adding a boolean that is kind of like will halt, but is like, it's more about right now versus sometime in the future. And the other thing I could do is like just start pulling some of this out into functions. Like this could be a motor halt function pretty easily. I would just have to remember that that also means don't run any of the rest of this. But yeah, maybe it is time to just start pulling some of this out. Like this could easily be a separate thing. It's just one of those readability decisions. Like, if I could actually turn this into easier to read code or easier to maintain code through careful abstraction, then that would be nice. If it's just slicing up a long function into a bunch of short functions that are still spaghetti, then it's not actually helping. So it's kind of a stylistic choice, but also kind of a trap. I think I'm going to change will halt into halt soon and halt now. Oh, actually, will halt is... Oh. That's really just asking, is my velocity target close to 0? And the main reason I have this organized weirdly is just because I am still fundamentally mistrustful of certain aspects of using floating point for control flow. I just wanted to be sure that the comparison happened up here, but then I could also override it with these comparisons. Mostly out of paranoia. Yeah, there's a couple of things we can at least pull out of here easily, like this quantized motor controller update stuff. Like this right here. That seems like an okay name for this. Let's put this above so we don't have to declare it, because I kind of prefer that style. So now this is just responsible for taking a floating point PWM, clamping it, quantizing it, sending it to the hardware, turning on the H bridge. Cool. This is what we definitely skip if we're halting. So by contrast, we also want this to be static, which in this case means that it's not visible outside the file. Yeah. These functions are not going to worry about the timers, because I think I still want the timers to be local to this tick function. But these can at least deal with some of the results here. I'm going to say output halt, because this is really very, very specifically about the output. Well, actually it isn't. It's about the whole control loop. Okay, just halt then. I might also call it something like reset, but reset is also very vague. And halt is nice and physical, like it's not going anywhere, we hope. I'm just hearing the 3D printer, which reminded me to check on it. This is actually the last WinchBot shell. There are a couple of other pieces to print. I still need a handful of wall mounting brackets. And I think I need to print some new pulleys. You know, little stuff like that. But these were the really big pieces, and it's close to done. Is that a good cat? More cat. PWM halt. Now I'm also thinking about what happens like immediately after this. So we do the halt. That resets all the gain, or all the state for the control loop. It's gonna kind of cycle. Like if there's a jam in the sensor, then this would cause it to start ramping up the motor, and then as soon as this jam detector triggers, it would just kill it immediately, and then it would just start slowly again and just keep tick, tick, tick. So we should see something like that. We might want some kind of other timer in there to slow it down, but like as long as the motor is not making very much progress, that's fine. But the other thing I might imagine doing is kind of feeding this into some like halt countdown timer. So what this is saying, this is sort of going into this sort of heavyweight halt logic, like turn off the whole H bridge if it's detected that we're not responding to a command to go to 0. And the expectation here is that, well, we're being commanded to 0 anyway, so as soon as we clear whatever state was stuck in the control loop, then we're going to make it there. The force limits already have that behavior where if you're up against a force limit, you can get it into this kind of oscillation where it kind of like runs up against it and then it backs off, and then it runs up against it and backs off again. But that hasn't been doing it very, like it's still pretty soft about it. Because the ramp up rate is pretty slow. That acceleration ramp rate is a reasonable solution to this problem, maybe. Because if we zero that out, then it's going to take, we're going to have like a slow approach back to that again. The other thing I can imagine doing is having a specific lockout where we say, okay, we're not even going to try to move the motor for a certain number of clock cycles. I think we can move these watchdog timers into their own separate little functions too. Let's try that. How long do I want to make these function names? Winch command receive timeout. I want this to be like a predicate, like if winch command or receive timeout, but I kind of had this like winch underscore naming convention. It's like they're static functions. It doesn't really matter. They're not visible outside this file. But I was trying to have a little bit of consistency in this C code. Oh, how about winch command timeout check? That solves my problem. So we're reading the counter that gets written elsewhere, in this case by the network interrupt, updating this local tick counter. And actually check doesn't specify what the result actually is, but expired would is expired. Okay. Let's try that. Oh yeah, carving up the control loop. Oh, excuse me. If this was in a slightly higher level language, then these functions could have a lot less repetition, but this seems to be what's convenient right now. Okay, so then the force limits here. Let's also pull out that velocity being close enough to 0 predicate. And I'm not going to prefix this with winch because it seems like I'm not using any of the global data here. This feels less like a member function and more like a static global for whatever kind of object model you want to imagine goes with this code. I guess I could use absolute value. The reason it matters that it's velocity there instead of just being a number that's near 0 is that's really how I choose this threshold. This is specifically saying that if on either side of 0 it's not more than 1 times 10 to the minus 3 meters per second, I just don't care. And we'll treat that as 0. I guess specifically what I'm saying here is that I want any value that is that close to 0 to have the ability to stop the winch even if the control loop is not responding. So then let's also pull out these force checks. Isn't refactoring fun? You just clean up all the mess you make earlier. So this is, like, we can basically just assume that we'll just have an if statement that's like, if winch for first timeout is expired, or blah, or force is out of range, just any of those, then we go through the halt conditions. Okay, and this actually depends on the velocity target. I think it's safe for abstraction's sake to have that read from the command again. I'm not going to worry about passing that in and capturing it like that. So we want the filtered force and oh, maybe we do want to capture the command there, because we actually, I was careful to grab this local copy of that whole structure, because I only wanted to read it once per tick. I don't think that actually matters here, because I don't think it could ever be modified by anybody higher priority than this interrupt. So I'm just not going to worry about that. Yeah, I don't know. The part of me that's particular about C code doesn't like that. It doesn't matter. Let's just keep this simple, not overthink it. I'm like, I don't want extra loads in stores, but it doesn't matter. It actually really doesn't. Yeah, where do we use that? Because like a lot of that is capturing the force limits that we're using here. And there's the accelerate. Here we didn't even use the captured version on diff filter. That's great. Or down there. Yeah, okay, whatever. I'm just being unnecessarily and completely unhelpfully pedantic here. Let's just remove that. Let's just I mean, I think some of these actually I just want to have a local variable, but right here I'm just going to localize the force stuff to this function. And so the max, so this is also something that I've considered changing, because right now the max and the min only apply conditionally depending on the sign of the movement. So if it's over the max limit, you can unspool the winch just fine, and if it's under the min limit, you can still spool it up, which is often fine. But especially if it's pretty far under the minimum limit, then it might be safe, like unsafe to run it in either direction because it might be tangled. This might need some modification later, but I think I'm going to mostly leave it like this for the moment. Right. So maybe now the jam detector. Let me start putting some of this back together. I feel like now I'm making a giant mess and I need to start controlling it. So winch PWM halt. And timeout, force timeout. I don't know if I want short-circuiting logic here. I actually think I want all of these to be independent because I want the counters to still run. So, in case you're not familiar with this, if you use, in most languages actually that are derived from kind of C-style operators, these binary operators will have kind of a short-circuiting feature where if, for example, this is OR and the first operand evaluates to true, then it doesn't need to know what the second one is, so it won't evaluate it. So it doesn't affect the results, but it affects the side effects. So in this case, we wouldn't end up updating the counters, for example, for is the force sensor working, which isn't bad right away, but it means that if there's something complicated with multiple faults, then we might end up kind of going back to what seems like a working condition when it isn't actually working. It just seems easier to reason about if these all run separately. Now I kind of want this function velocity near 0 to have a better name because I wanted a variable to have that name. Who needs to know about the velocity being near 0? Actually, that's a test that I'm happy to short circuit out of. So maybe it just doesn't go first. Yeah, I don't know. Maybe the short circuiting is fine. I just need to put them in a careful priority order. I'm just imagining the code writing all these separately and assigning them into separate variables and having that be kind of annoying looking. I could use binary operators because they don't short circuit, but that's kind of a weird hack. Or bitwise operators, rather. Yeah, let's just change this. I'm going to be less pedantic about all this floating point nonsense. Okay, let's not worry about that yet. And then maybe something just more like that. It's tempting to even just put these on the same line. I know some people don't like it, but I like it when it makes something that seems tabular in my mind look more like a table. And this is winch force out of range. These are actually all, these should be 0.0f. I know the compiler will convert it, but I like using the right data type. So we got that taken care of, and that. And let's Let's add the jam detector. So this is getting back to the problem we were having before. The winch jam detector isn't really something that should be just setting the velocity target to 0. That should be actually halting the motor. So that kind of runs at the same level as the halt detector. So this doesn't need any of that. This can be pretty separate. Okay, let's put this separately too. Oh, this needs a name. This needs the velocity target. So this will be a function that takes in this velocity target, which, could be 0, could be non-zero. This is just whatever the input to the control loop is. And it'll return a Boolean that if the velocity target has been 0 and the output is not going to 0, then that'll just flip to true and say you need to stop. Now I think this might be the place where we call this its velocity near 0 function, and then we just deal with the floating point elsewhere. This keyboard connection is the flakiest USB in the shop right now. That comment doesn't make any sense anymore. I can rewrite this. Oh yeah, and we only need to run that test if the motor is trying to drive, so we can swap the order there. Here's an example of where short-circuiting can actually help save a little bit of CPU, which completely doesn't matter, but makes me happy. Yeah, so in that case, we just want is velocity near 0. To count. Okay, I was also tempted to put the return in here, but I'm going to let the compiler figure out that this is going to be always false in the false arm of this. I think this is the nicest way to write this. I find it so relaxing to write Rust code and to be more confident that when I write the code, the compiler is going to do something reasonable with it. Whereas I feel like I try to micromanage a lot when I do microcontroller code in C++ and C. But maybe that's just because I feel familiar enough with it that I enjoy that process. With Rust, it's still new enough that I'm not really sure what to micromanage, so I can just relax and not do it. Not worry about every load and store and every data hazard that might show up. Great, so now I think this would be something more like winch needs to halt or jam detected. Okay, so we want the motor to be commanding above this PWM threshold, and we want the velocity to be below. Where did the actual velocity go? Winchstat.sensors. Cool. Okay, and this will just increment the timer, and when it's over this duration threshold, then we return true. Alright, winch jam detected, or winch needs to halt, then it should stop. Although I don't want the short circuiting here. I also think I want to put all that below here. So this is setting the velocity target based on error conditions. Then we're doing the ramping. Reset the keyboard. Okay. That's kind of nicer. That seems nicer. Let's see if that compiles and then see if we can test the new features. Oh, Ben asks, did I miss flying toolbox? I wouldn't say that. I have a flying spool right now. I had a flying toolbox a couple days ago. Yesterday there was a flying bucket. Actually, this morning there was a flying bucket. There was a photography crew here this morning for kind of an unrelated thing, kind of a photo shoot for a mill company I like that I was helping out with. And they were they were set dressing a little bit and didn't like the bucket. So I swapped it back for the spool. Alright, let's see if this compiles. Oh, look at all them errors. I think I might have forgotten the sensors struct in there. That should be bool. That should be bool if I could type. Oh, do I not have that? Was I right to doubt this? Yeah, I mean, well, okay, maybe I can have it if I bring in math.h, but I'm not gonna hold my breath. Oh, did that maybe that did it. Well, I'm gonna believe it when it links, but sure, maybe we have a math library on this platform. all the people who were born in this century are like, who's this ancient relic who still wonders if their math works when they program? This is just one of those things where I know I could just keep it all in registers, but it's just going back and forth to SRAM all the time, and it's fine. Actually, there was a little Twitter discussion on that earlier. Well, I was reading this paper, really cool paper. I am forgetting the names of the people involved because I'm terrible with names, but I think I saw the link. Actually, maybe Piotr first pinged me about it in chat, and then I also saw it on Travis Goodspeed's Twitter, and it's a paper with some really delightful sets of techniques for getting past the code readout protection in STM32s, and it's just like delightful stuff. Like oh, you can just take SRAM snapshots. So this is related a little bit to the thing we did a while ago with the Tech gimbal and reading out the bootloader key in SRAM, and you know it's protecting you from reading out Flash, but you can read out SRAM just fine. So they use that to say, hey, well, you know, you can actually get a lot of information about what's going on and potentially some really useful, very short-lived keys if you just keep taking SRAM snapshots every clock cycle and then run the experiment with different delays. So it's a really good paper. I recommend it. Yeah, can I give you a more specific link? Because I hate being like, here's a great paper, I'm not going to tell you where to find it. Let me see if I can give you a specific link. I just tweeted a link to it, so maybe, or actually, no, maybe I didn't. I tweeted a screenshot which should have enough information for me to find it. Yeah, Woot 17 Obermeyer. Yeah, this stuff. This is great. So this is what you should read if you want to have a great time. Shedding too much light on a microcontroller's firmware protection. This is just a masterful piece of work. Super fun read. Yeah, Johannes Obermeyer and Stefan Tachner. Yeah, it's so much fun. There's this cold boot stepping. There's this we might have to try this out on stream. Like, this would be super fun. There's a race condition in the debug port. And this seems like the kind of thing where, like, oh my god, why did I not notice this? Why did the designers not notice this? So like maybe it's only on like one series of these chips, but it's the stupidest thing. Like, you can read Flash despite the readout protection some portion of the time, depending on the bus access patterns. And the reason most people don't notice is that the software debugger is like, oh, you're not allowed to access it, and it exits or something. It doesn't just keep trying. So, great paper. I highly recommend it. I had fun reading it this afternoon. Oh yeah, and of course, they need to map out where the protection bits are physically, because of course part of their technique is going to involve ultraviolet light and lasers, and so they're just using the sensor, or the patch of RAM, memory itself as a camera to figure out where the light's going. So yes, very fun. What else we got? Just a couple mundane errors. Inch stat. I'm just reading these things out of RAM all the time. It's fine. Oh yeah, so the reason I was remembering that paper is that there is a technique that involved, because you're doing all these RAM snapshots, well, if you have a bootloader that is running a CRC over the code, because that's really common in a bootloader because you want to see if the code programmed correctly. So you run the CRC, and then if it keeps any intermediate state for that CRC in SRAM, so whether it's like bytes of program memory or partial CRCs, it doesn't really matter what it is, that's enough bits that you can get the data out. And then I was feeling kind of skeptical of that, like, oh, well, sure, like if it's some kind of cryptographic thing, that's going to overflow into SRAM, but if it's just a CRC32, that seems like it would stay in registers. So I don't know, I'd be interested. That'd be something where it's kind of nerd sniped me, like I want to sort of pull at that thread and see, like, okay, let's grab something off the shelf, like, oh, maybe something we already reverse engineered, like that gimbal, and see, well, actually there is a CRC in there. I think I've already got an IDA database with its CRC annotated. We could go take a look at how much of that gets stored back to the stack as it runs. Oh, nice. Robert says in chat, by the way, a similar trick was used by somebody to redump the Game Boy Advance BIOS. Basically, the lockout there didn't take into account prefetching/pipelining, and so it was looking at an old program counter value, and so the redump was done by basically applying return-oriented programming techniques. That's cool. Oh, MIDI key to frequency. Yeah, so the Game Boy Advance was kind of interesting, because, like, it had all of this semi-privileged code that you could jump to in ROM, but it was just like such a wide interface, and it had like mem copies in there, and they tried to do things like check the range of the mem copy so that you can only access certain kinds of memory, but I feel like there was some kind of loophole in that we took advantage of at one point. Yeah, the GBA BIOS is a thing. Command. Oh, did I not try to rerun that? I keep getting distracted by talking instead of compiling. What kind of programmer would I be if I talked instead of compiling all the time? Did we already pull the velocity out somewhere? Oh yeah, it's up there, but that's fine. Witch stat. If only it was a witch, or a sandwich, either kind. Although I'm pretty satisfied having a stack of winches, I have to say, as much as it would be nice to have a stack of sandwiches. Having whatever I designed has been nice. Do we trust this? Let's turn on the camera, just in case this destroys itself. I'm gonna see if I can get a little bit of extra light on this scene. I'm like just barely out of frame. It's fine. Oh, that is not amazing. We can do better. had this little light panel. I tried just putting it in the hot shoe, but I think this really needs to be positioned somewhat better. That's better. Okay. Let's let her rip. If my keyboard works, that was undramatic. And well, you can see the little green LEDs come back and the sensors are updating again. Joystick went to sleep. Oh, what's that? I think that was just the spool bouncing against the tripod. Oh, there's a cat super interested in this winch. I'm gonna have to be careful. Good girl. Get you on. I love how curious this cat is. She just seems so curious about all the little pieces moving around in there. Hey, girl. You just want to touch that, I know. I'm not really gonna let you. Super cute though. Oh, she's super interested in that. You gonna help me test these sensors? But here's the feedback if I just, so I'm not touching the controller right now, but if I just spin that, it's gonna try to maintain the position, sort of, but not very well. Let's try this new safety feature. So I'm going up. That could have worked better. It feels like it kind of cycled a couple times there. What actually happened? It certainly ramped up a lot. Yeah. I think we need to make that a little tighter. Like, that's certainly not going to stop it if something actually goes wrong. Oh man, that's such a good view of Luna, though. What a beautiful cat. Oh, she's so pretty. Her friend Cloud is down here on the floor now. Slightly out of frame. You might catch his tail. Aw. So this morning I noticed Cloud limping a little bit. I think he sprained his wrist. So I've got a close eye on him, and I'm going to take him to the vet unless it starts getting better tomorrow. Yeah, all cameras will be cat cameras, basically. Well, maybe she's off elsewhere. I have no idea what she's doing now. Okay. Let's see if we can just tighten these parameters a bit. So I think we should make this duration much shorter, because this is like the kinds of thresholds here. I think maybe the problem is, I think it's not something we want to do kind of clock cycle by clock cycle, but it's like kind of a circuit breaker. Like if it trips, it should stop it for a while, I think. I mean, the assumption here is that it's probably a problem that requires an operator to come in and poke something. So it's probably like an actual jam, but you don't necessarily want it to stop completely if it's a false positive. Yeah, let's have another thing that's like a halt lockout duration. And I think if we halt it for either reason, we should just not try to start for a minimum duration afterwards. Yeah, basically what Blake just said in chat, like a limp mode. And I think that should probably be common to both the jam and the halt, which are kind of different. Motor halt restart delay. Let's make this a half a second. It could even be like an entire second. Half a second is probably fine. This might not happen super infrequently when you're manually controlling the winch, because if you're just manually moving it and then you let off the controls, it's probably going to halt unless we have the PID loop really tuned in. But it's not going to halt like especially hard. Like it's just going to kind of start ramping down and then just cut off and coast, and that's fine. But it shouldn't do that when it's under active, like, closed loop control with the whole system operating. I do want this to be shorter, like 1/10 of a second. And make this a little lower. I don't want this to be so low that, well, yeah, what is the danger in making that too low? If it's legit not moving very fast, like the false positive is mostly if it's just not moving quickly, which you want to distinguish from being completely jammed. But at, unless this PWM level got pretty slow, like what kind of PWM level does it actually take to sustain very slow movement? So what are we actually dealing with? So here's some movement. What is the actual speed there? That's like 1,000 counts per second. At a PWM of like 0.2. Let's try a PWM of 0.3 and yeah, I think these are probably fine. I think it just needs a short duration. And the velocity is going to be really noisy here, so this might end up being somewhat, like this is basically peak velocity, which is, with all this noise, kind of a tenuous concept, but I think, maybe like 800 or something like that. This is also quantized, because you notice it seems to change in kind of large chunks, and that's the encoder ticks being multiplied by that 250 hertz. So that this velocity is actually number of encoder ticks between control loop, like encoder units between control loop ticks multiplied by 250. So yeah, 800 seems like a decent number there. Let's just try that. And motor halt restart delay. Something like that. A little timer. Let's see if those times are anywhere near what I want. It's always such an experience flashing a robot with new firmware. That seems fine. Let's get some graphs on the screen and see if I can trigger this safety feature again. Yeah, that's what I want. It's like, whoa, something's wrong. Now the cat's interested again. You don't want to be that close to it while it's moving, Luna. Oh, she is so shiny. Oh, yeah. I taste it working good now. Yeah. Totally. Tuco, are you confusing the autofocus? Or Luna? Oh, that's embarrassing when you call the cats by the name of the other cat. Oh, okay. Can I get both of you in the frame? The winch bot and the cat. I guess I'll leave the graphs on screen because they're kind of interesting, but I know the cat is interesting too. So, here it is moving very slowly. Here it is with a sticky capstan. Yeah, so you can see the capstan was still moving a little bit, but just by causing it to be kind of sticky, it was hitting that algorithm. Let's see if we can get it to give us a false positive. Just trying a range of speeds going up and down. It seems good so far. What was that? I mean, I think some of this is just like the PID loop being a little wonky still. Some of that kind of oscillation. Okay, well, so the one part of this I think we haven't tested is the force sensor watchdog. How can we make the force sensor fail? I might just try shorting out the data bus with some tweezers. That would be a little easier to get to if I took the other cover off. Oh, hey, Cloud. Okay. Oh, geez. Luna is growling at Duke. Hey, Luna. All right. I think this is about one of the last things I'm going to do. Let's test this, and then I think I might wrap up the stream because it's getting kind of late here. But I want to see if all these little safeguards we added to the firmware are actually working. So I'm just going to try shorting the clock and data together, which should keep the force sensor from reading successfully. Did that work, or was that a coincidence? I don't think that's working. Let's take a look at the actual data. There's our force sensor. Can I perturb it? That'd be easier to see once the graph rescales. All right. That was a spike up to 7 kilograms when I shorted the data and clock. Didn't seem to actually cause that much of a problem, though. Maybe these tweezers are not very conductive because they might be covered in grime. Let me try a different thing. Okay, maybe that's not working. Maybe I'm gonna have to trace this wire and figure out the right one to unplug. Maybe it's easier to look up the documentation. Okay, so I could unplug either of those, PQ0 or PQ3, and I can just look up what those are on another one of these boards. Okay. It is. This power supply is pleasantly warm. If I unplug this yellow wire right there, we should have the right effect. Okay. I guess that did not cause a flow control issue. That just gives us bad data. What is that actually reading? It's just reading 0. Yeah, so maybe we want that to also treat 0 as a potential problem, even though that's a real potentially valid reading. Like 0 is fine. If we get a bunch of consecutive zeros, that's a pretty bad sign. So I think that's probably something we should factor in. See that there's some glitches there. So I think that was the data line being unplugged. Let me try unplugging the other one, the clock. Yeah, okay, now the counter goes out. So if we lose clock, we lose flow control. If we lose data, then we only lose the value. So we do need to check for zeros. So now I can't control it, right? Yeah. Okay, well that's good to know. Let's make that change. And then maybe I'll wrap this up. So... let's just have this count time since the last non-zero force measure. We want to make sure, well, it's not technically what it's doing. It's the last time since we've noticed that the force has changed, and the most recent force measure is non-zero, is I think the way I want to code this. Okay, I think that'll do. Sometimes I would see some measures that weren't quite 0, but it was so close to being a stream of zeros that I think this will still work. If we wanted to get complicated, we could look at the Hamming distance or something. Okay. So you can still get it to sort of move on its own if you give it some phantom force feedback, but only to the extent that, like, it'll hit that halt watchdog. So if you do it enough, because you're not actually sending it a velocity command. Anyway, what are our tests? We just wanted to move this and try disconnecting the force sensor. So we've got this. That works nicely. Let's try the other thing. Yay. I'm happy with that. Okay, let's get this checked in. I think this is a good stopping point for the night. About fine for now. Oh, yeah. All right, everything's in Git in case you feel like playing along at home. There's a repo in the Tuco Flyer organization. It's got a picture of my cat. It's got the firmware. It's got the control software written in Rust running on this PC. Got all the CAD models. So I'm gonna wrap up here and get ready for some sleep. But I'll see everyone soon on the internet. Thanks so much for dropping by. Hope you enjoyed the cats and the robots. And a special thanks to everyone who's helping out by telling their friends and showing up in chat and just generally being a good neighbor. It's pretty awesome, and I appreciate having you. So, yeah, Blake says this cat show is remarkably short on cats right now. What happened to that? Actually, we've got one right up here. Robert says you might be able to short out the load cell itself. I wouldn't expect it to go exactly to 0 if I did, given that this is a 24-bit A to D, but that might be a good test to try. I think right now I've covered most of the failure modes I care about, but it could always be good to add more. A test page in the UI to inject data. Yeah, that would be interesting. It's just the problem is, like, I can do a lot of stuff in the UI that's kind of within the bot controller Rust server, but if I want to do anything within the firmware, I've got to kind of do the plumbing to get there, which involves getting it to and from the robot via those UDP packets. And right now that protocol is actually very simple. There's only a few different kinds of packet types, and we could add more, but I've been trying to keep it simple unless there's a good reason to make it more complicated. Luna's growling now because Tuco's close by. Oh, this tripod. There we go. I'm running out of cable. This is maybe not the camera to be doing this with. I hope you all enjoy this chill girl half as much as I do. She's sure a beauty. Oh yeah, just responding to Blake's question in chat. Yeah, the reason I can monkey with the PID value so easily is because they're going out to the firmware inside of every motor update command. So it's just kind of the structure of the way it is. Like, I could design something where that command included some sensor overrides maybe, but they would really only be useful for this specific circumstance, and it would have to kind of be in the protocol into perpetuity unless I felt like versioning it again. So, just one of those little convenience trade-offs. Autofocus is having trouble with this cat. Black cats are so hard to light, but they're so rewarding when they're lit well. Alright, I think I'm going to actually sign off now. So, yeah, thanks so much, everybody. We'll see you all next time. Happy hacking. Hey, Took. You know, maybe one of these days I could click the stop button on the stream. I'm used to doing post-roll, but then sometimes I get carried away. Anyway, I'll see everyone later.